Welcome back to the Ephemeris podcast. I'm your host, Aphelion. As always, thank you very much for tuning into this podcast episode. I appreciate the love, especially considering the amount of views that I got on the last episode. I genuinely appreciate it. And for me personally, I've had a good week, but we're not going to get too specific or take too long talking about that because I have noticed that the viewer retention tends to go down after a minute. So let's get right into the contents of this episode. And yes, it is the episode that has been waiting for way too long. I've decided that the LBV episode simply cannot wait. So we're talking about that today. The big last piece of the variable puzzle that we will discuss. So, RR Lyrae and Cepheids are variables that I did not cover in this little series, I guess you can call it. Mostly just because they're very well known and they're not too interesting, just very well defined period luminosity relations, and we kind of already know about like general variability and how that works, and that's the case with RR Lyrae and Cepheids. So I'm going to leave that out of this series. Perhaps it'll come back to us at another time where we can discuss it in a little bit more depth and bring some interest to it. I would like to bring interest to those variables before I kind of talk about them in an episode, just, willy-nilly. So, LBVs are what we're going to focus on today. They're another extreme of kind of variability that I'd like to discuss, and what LBVs are, to begin the introduction of these things, Luminous Blue Variables, just to expand that little abbreviation that I'll be using for the rest of the episode. So they're blue supergiants that are unstable. And discussing blue supergiants, we already know they're crazy, right? But they're about to get even crazier. So the pulsation of LBVs can be one of two. They can be periodic outbursts, or they can be eruptions. And if that's starting to intimidate you, that crazy vocabulary, it's because these stars are intimidating. The smallest of these stars are 2 times the temperature of the sun, which is like 10,000 Kelvin. But the biggest of these stars are 5 times hotter than the sun. That's 25,000 Kelvin. That is mind-blowing. Like, if you could imagine that there are planets around such a star, and I'm not saying that's anywhere close to possible, right? But if you can imagine, they would be burning. Literally burning. Like, Mercury reaches a maximum temperature of around 800 degrees Fahrenheit, being that close to the sun. Imagine what that would be like if it was the same distance, but Mercury to an LBV. Like, that'd be crazy if it could exist. Again, it's nowhere close to possible, right? And even being Neptune's distance from the sun away isn't any better. You would have to be Earth's distance from our closest neighbor star, Proxima Centauri, away from an LBV to be anywhere close to a semblance of safety. Because that's where the emissions tend to kind of fade out. But yeah, it's crazy. That's probably not even enough, though, to be honest. And on top of these stars being hot, they're also extremely luminous. And you might be saying, oh, whoa, thanks for stating the obvious, but seriously. The smallest of these bunch are 250,000 times more than the sun. Biggest of the bunch, 1,000,000 times. Like, if looking at the sun blinds you, these stars will not only melt your eyes, but they will melt you as a whole, right? Because they're hot, they're luminous, they're crazy. I don't want to get too caught up in the numbers again, because we already know it gets wild whenever we do that, right? So they have a damn good reason for being called luminous. And it's a very good reason to be far away from them. Thank goodness we're not close to any of those. But anyways, I digress, right? So 2 types of pulsations, outbursts and eruptions. When these stars aren't doing either of those 2, they're known to be in the quiescent state. Hopefully I'm saying that correctly, right? In this state, they're typically B-type stars, which, looking at an HR diagram is going to be pretty extreme. It's going to be in that top left corner that we've talked about a little bit with blue supergiants, right? So once these LBVs exit their quiescent state and undergo outbursts, the expectations for these stars would be they go up in luminosity and then they shift slightly in spectral class, and temperature is maybe, it depends. However, this is not the case with LBVs. Their bolometric luminosity, which is just like how we measure its luminosity in the most common form, right? That doesn't change, but their spectral class actually shifts very significantly, around 1 to 2 types. So if it starts at a B type, it'll shift to either an A type or an F type, which is kind of lower on the scale. And the temperature drops. It drops pretty significantly. And this kind of what we'll call outbursts, they cause a visual magnitude brightness increase, which, to us matters because, visual magnitude is something we have to think about when we're observing these kinds of stars. And if you're wondering why these are called outbursts rather than pulsations with all the other variable stars, it probably has to do with mass loss, which we'll talk about a little bit more with the eruptions and, that kind of jazz. But obviously don't quote me on that. I'm just throwing that out there. So those are outbursts. Some stars have stronger outbursts than others, and this is called a strong active cycle, and some don't, which are weak active cycles. And I think that difference might become a little bit important later on, but again, that's just another fact that I'm going to throw out there. All right, so what about these eruptions? This is where the CRAZIER indeed gets craziest. Eruptions for LBVs involve huge mass loss and actual changes in luminosity versus, outbursts, right? And in fact, these eruptions tend to be so large that they used to be mistaken for supernova, which makes sense. You got a huge star that's erupting, it's losing mass, it's ejecting matter all across itself, and then it's dimming a little bit, right? Sounds kind of like a supernova. And they also, these eruptions create an emission nebula, which makes them quite a sight to see. If you look at some of the images of AG Carinae, or you look at, there was this recent simulation that was created for LBVs that it creates quite a colorful picture of the stars themselves when you simulate them, right? So those two things, they make they make to be pretty photos because of the cool emissions, right? Okay, let's take a breather. Let's recollect. That was a lot. We know what kind of stars LBVs are. We understand its variability a little bit. Now all that is left is why, because again, it's the Ephemeris podcast. We gotta know why, right? If you listen into the SRV episode, we talked about a model of pulsation that's very common among most variable stars. And this is actually, it has a name. It's the Kappa mechanism. Or at least, what we described in the last episode resembled something like that. However, LBVs do not completely align with the Kappa mechanism. And before we get carried away by this fact, let's be honest. We have reason to believe that because we've seen how LBVs are different, right? So what is the next best theory? The variability of LBVs has something to do with the Eddington limit. That's the next best theory. So what's the Eddington limit, right? We don't know anything about that. It's the maximum luminosity a star can achieve when there is balance between the force of radiation acting outward and the gravitational force acting inward, right? So it kind of caps how luminous a star can be before, you lose the balance of the forces. So essentially what this theory is saying is that LBVs become unstable when that limit is crossed, or something along the lines of that, right? And it makes the most sense because this limit manifests itself on the HR diagram as the Humphreys-Davidson limit, which is the coolest temperature a highly luminous star can achieve while keeping stable. So there's that theory for you. But before we wrap this thing up, because that's really the most conclusive theory we have about LBVs and their variability, right? So before we kind of wrap this episode up as a whole, I do want to talk about what happens next for LBVs, because as these stars go through instability and mass loss, something has to change. They can't just keep doing it forever and ever. There's going to have to be some evolution in there. So how do LBVs continue in their stellar evolution? Well, the very likely path that we've seen for LBVs is becoming a Wolf Rayet star. And Wolf Rayet stars are less than massive, but highly luminous stars that, in their classic form, have lost all their hydrogen and have broad helium lines along with either nitrogen or carbon emission lines. Or sorry, yeah, I believe they're emission lines, not absorption. So the reason why we're able to identify these characteristics and know all of this about Wolf Rayet stars is because of its spectra, which we kind of went over what that tends to be for Wolf Rayet stars, and then stellar winds, right? But for the longest time, there was a dilemma for explaining the existence of these stars with just that, just stellar winds. Like, stellar winds themselves couldn't account for the lack of mass in these stars because wind clumping, which is pretty self-explanatory, wouldn't allow that to happen. Like, it wouldn't allow a mass loss rate big enough to explain why these Wolf Rayet stars are like only about 20 solar masses. But with the discovery of LBVs, it would make sense that Wolf Rayet stars would evolve from them because their LBV phase, if we assume that's the case, right, it would explain the mass loss. So basically what we're saying here is because we see a perfect connection between LBVs and Wolf Rayet stars, that's pretty much what's next for an LBV, right? Blue giants that become unstable and vary through outbursts and occasional eruptions will turn into Wolf Rayet stars and end up dying as a supernova, because we know that Wolf Rayet stars are likely to become Type Ib supernova. So there we go. We have the complete stellar evolution of an LBV. And there we have it, as a whole. Ladies and gentlemen, that is the luminous blue variable, and that concludes our investigation into variable stars. It's been a pretty crazy ride. We really got to take a breather, sit back, think about it, right? We talked about our Corona Borealis variables. We talked about long period variables like Mira and semi-regulars. We talked about how crazy those can get in terms of stellar evolution, where they're at, what they do. And then we got to this really crazy part at the top of luminous blue variables, which involves the craziest stars, blue supergiants. And so that was quite a series. I found it pretty fun, even though, you know, as I mentioned, we did miss the more common parts of it, like RR Lyrae and Cepheids. But yeah, let me know what you thought of the episode on Spotify and YouTube, wherever you're listening. If you enjoyed this episode, definitely make sure to leave a follow on Spotify and a subscribe on YouTube channel, again, wherever you're listening. And yeah, that's all I have for you guys today. I did kind of expect this episode to be a little bit longer, to be fair, but I think it still had the meat and potatoes I was looking for in this episode. So yeah, until the next episode, I will see you guys later. Peace.